I think I'm going to get started. I guess I guess I should welcome you back from your wellness week. So I hope people are returning in a good frame of mind from last week, that you feel more rested, at least, than you did before you went into last week. We don't really have a lot left in the course. I would say we're in about week 9. I have a schedule that runs out to about week 14. Week 14, I think, is a review week, or if people tire of that, we'll probably talk about something new there that won't be on the final. But that's about what's left. And so, as far as I can tell, people are doing very well. I don't have any complaints about people's efforts. So keep doing what you're doing. People are turning things in. They seem to be responding to the material in a way that's very encouraging for me. As usual, I have a few announcements about this week and maybe next week. So this is week 9. You can check to see that week 9 is available. There's an overview there which describes a little bit about what's going on. So there's the usual reading assignments. Reading assignments this week are a little different because of the kind of material. They'll change back into something that maybe is more regular the following week. I feel like these reading assignments are basically just summaries of what's in chapter 16 of the text. It will turn out that chapter 16 of the text is, at least from the point of view of the theory that we're going to talk about, very important. So you can read it. I think you should view the reading assignments just as summaries of what you're seeing in chapter 16, as though it's broken up into 2 pieces. The first piece is a description of the type of mathematical model we'll use for the sort of work we're going to do this week. The second is associated to something called a confidence interval, or construction of an interval estimate, which we'll also talk about this week. So with the reading assignments, I guess all I really want people to do is something like this. Just read the chapters, read the reading assignments, just study the reading assignments for a moment and take notes on these things. And when you submit the result for the reading assignment, all I really want you to do is just type in the sort of notes that you happen to have, maybe with any questions that you might have over these things. So like I said, take the reading assignment seriously. It's probably not enough just to type in, I have no questions. Maybe you really don't, maybe that's okay. But most people, when they're reading this material for the first time, do have at least a couple of questions about what's going on that I can try to answer after you submit those on Friday. So does this make sense? Just read them. So there aren't, unlike the last couple of reading assignments, there aren't really questions where you're sort of writing down some kind of numerical answer or anything like that. Does this make sense?
Yep.
Okay. Good. Other basic updates, I think. Homework 8, I guess that's due next week, right? So homework's, I forget the numbering, but I think 7 is due on this afternoon, which has to do with the probability models. Homework 8 has to do with a particular model we're going to be using, and that's due on Monday at 5 p.m. So that's not really a change from what we've been doing so far. As usual, you can find the link to that homework in the week 9 course module. There's a written assignment 6. I'm hesitant to assign it, but I'm hoping that it's not too much work. So written assignment 6 is meant to just be an exploratory exercise related to the idea of a sampling distribution. So sampling distribution of sample proportion, that's what it is about. So that's due on Tuesday of next week at 5 p.m. Like I said, since next week, I'll talk a little about this in a second. Since next week's the exam, it's probably important to just sort of think a little bit about what we're doing. Think a little about the test this week, just to kind of get yourself mentally ready for it. I think the written assignment will help. But see how it goes. Tentatively, I think that's due at 5 p.m. next week on Tuesday. People find that the work's too much, or they want to devote more time to the exam, you can always let me know and I can delay it. I do want 8 written assignments this semester, and I think getting 6 in now, having nothing next week, and then having a couple of more after that will do the job. Giving us, a couple of weeks without any written assignments, so you can sort of sit back and point in the direction of the final exam for the course, begin to review for it. So the week after this one, there's exam 2. That's in week 10. The format of exam 2 will be similar to the format of exam 1. I will release exam 2 at 8 a.m. on Monday morning or thereabouts, and the exam period will end Friday night at 11:59 p.m. So that's a bit like how the exam 1 worked. The number of questions will probably be about the same, maybe about 14, 15 questions. I feel that that's probably doable. The format of, you can leave, but you have to make sure you can complete everything before you leave, I think will remain the same as well. That tended to work pretty well. I don't think that there were any major technical problems with the first exam, so I'm kind of hoping that that trend, that continues on exam 2, I guess. The content of exam 2, I think I put up a description of that in the overview, but just to remind you, it's also on the schedule that we have. So on exam 2, the content of exam 2 will be chapters 10 through 15 and sections 16.1 and 16.2 from the text, and that's it. We'll cover more than 16.1 and 16.2 this week, but that's all I really want to put on exam 2. So that's kind of where we sit in terms of administrative announcements. I don't really have anything more to say right now. Does anyone have any questions before we get into the material proper, I guess? Everyone okay? All right, seems so. Yes?
Yep, all good.
Okay, good. So just sort of keep paying attention to the overview. I think I'll probably make week 10 available, though minus the exam this week, but we'll still have to do some things next week because it's in order to sort of fulfill the content obligations of the course, there has to be a little overlap, but the stuff we'll talk about next week won't be on the exam. So this week, glasses are messed up somehow. All right, good. So this week we're sort of entering the end game of the course, though it's kind of funny to say that given that there are a few weeks left. The end game of the course begins with sort of a discussion of this idea of the sampling distribution of a statistic. I want to sort of briefly describe what we're going to do over the next few weeks in just very rough terms, very general terms. And then I want to spend some time describing what we're going to do this week. There's some exercises, I think, for today and Wednesday in the classroom handouts. I'll bring people in the groups, so it'll kind of have the normal feel. So I'm about to open, I guess I'm about to open the notes. Let me give myself a little room to write here. Okay, so I'm about to show the screen. I just want to give you an idea of where we're headed with this, maybe show you a quick example, which is related to a problem that that you've seen before. So at least when we start talking about this week. So the goal over the next few weeks is to estimate some unknown population parameters. So that's maybe how you can think about what we're going to do. Sometimes it's going to look like we're doing more than that, but really that's sort of the underlying logic to the next few weeks. And the basic examples we're going to consider look a bit like this. So, I mean, I guess just as a reminder, our assumption is that populations are characterized by some unknown numbers. And we're calling those unknown numbers, we're calling those parameters for the population. For example, you can have a population mean, the mean height of say, all Americans in inches. So population mean. For the sake of kind of getting on the same page, we typically denote the population mean with symbol mu. There's also something that we'll call the population proportion. The notation that's used for that in this text is just the symbol P, it's the letter P. An example of saying something about a population proportion, if you remember ads from, if you're familiar with ads from decades ago, people who would sell toothpaste would often say something like, well, 7 out of 10 dentists prefer, the brand of toothpaste that you're selling. 7 out of 10, that's 0.7 as a proportion. So What they're saying is that we think that roughly 70% of dentists prefer Crest over some other brand of toothpaste or something like that. That's a pretty common way of trying to convince people to buy one toothpaste over another toothpaste, because you're sort of appealing to a group of I guess, experts that seem to favor one option over the other. But again, we're imagining that the population of dentists across the US has some sort of opinion about this. There's some unknown proportion of them that prefer Crest over some other brand. And we're saying that it's 7 out of 10, that it's 0.7. So probably what someone has done is they've constructed some survey. Or maybe if you're constructing the ad copy, maybe you haven't even done that at all and you're just claiming it. That's also a possibility. But in this case, that population of dentists would be thought to have some opinion about things. You don't know quite what it is. And so how do you kind of get out these parameters? We don't know them, but we're assuming that there are actual numbers out there to discuss, that there actually is a certain proportion of dentists that prefers Crest over some other brand, that there is a mean height to discuss in inches of all Americans, things like this. We don't know what those numbers are because we're not really running a census, but we can estimate these parameters by coming up with a random sample. And then using that random sample to come up with the value of the estimator. So in a class like this, sometimes, most of the time, you don't call what you're doing an estimator, you call it a statistic. In a class like this, when you have the idea of a statistic, you have the idea of the estimator, they're kind of the same idea. For examples, I guess, the sample mean, and this is typically denoted with the symbol X bar, or at least letter bar, estimates the population mean. That estimates that. Another example, the notation, and this is sometimes a little confusing to try to remember, the sample proportion estimates the sample proportion, and I think the notation in the book is this p hat symbol, estimates p. So again, the underlying assumption is that there is actually either a mu or a p to discuss, and out of the sample, we get a realization of the estimator. So we have a value for X bar, and the value we get for X bar represents a point estimate, say, for mu, or the value that we get for p hat represents a point estimate for p. So before I move on, and there are some others we'll talk about the difference of means and the difference of proportions. It's kind of where the class ends. There's really kind of only 4 more things to discuss. But the idea here is that we have the idea of an estimator. We use the estimator to come up with a point estimate for an unknown parameter. Is everyone with me so far?
Yep.
Is this all right? Okay. So when we do this, there's sort of one troubling fact, and we can kind of ask ourselves, at least right now, at least speculatively, there's kind of a troubling fact. It's not really, turns out not to be that troubling. If we take many estimates, we take many samples, let's say of a fixed size, we're going to get many estimates of the same thing. Now, it's not the same parameter, the same thing. So I guess if we're trying to say something about, and we'll talk about this example from written assignment 4 in just a second, I want to treat people's suggestions there seriously and talk a little bit about like what they might mean. But I guess intuitively, if we sample or we choose a random sample of 100 people from a population, and simply ask them whether or not they prefer Crest over another brand of toothpick. Maybe we don't even think of dentist. If we ask 100 people, maybe I get like 61% of them prefer Crest. Maybe you get 57%. You can ask the question, who's right? The answer is, in a sense, you're both right. And if you have 100 other estimates, we're going to get many, many other estimates of the same quantity. One can ask, how might those estimates vary? How might? Yes, Colton.
Would this, in a way, be almost like an observational study to see how different groups of people respond to the same thing?
Yeah, I mean, we're trying to get at that, right? And so you can ask. I mean, so when you're thinking about what if you're thinking about doing the same experiment many times, in a way, you're thinking about and gathering the data to kind of see what happens. It's almost as though you want to do a meta study, where you have many different lines of evidence which support one or the other, or some other theory, or some collection of estimates. So for us, we're thinking about, we might be thinking about something even simpler than what you're suggesting. Like it's natural to think that you can get many different types of estimates of the same quantity. And this might be a troubling fact. Like you might worry about the fact that I get one estimate, you get another estimate. Is that bad? The thing is, it isn't bad. In fact, it's totally inevitable. Under this sort of theoretical framework, it's that the estimates that we're getting vary, but we're lucky. I guess I'll sort of finish this with this. The estimates we get vary in a predictable way. And so it turns out that they vary in a way, at least with certain conditions being satisfied. And we can use this information, the fact that the estimates vary in a predictable way, to sort of step up or improve our estimation techniques in a way that we'll talk about later this week. So with that in mind, I mean, I sort of hope people kind of see where we're at. And I'd like to return to a problem that you worked on a couple of weeks ago. I mean, it seemed like I'm kind of obsessed with the idea of coin flipping. I mean, I don't think I'm unduly obsessed with it, but it's a nice example. And the coin flip example that you talked about in written assignment 4 is similar to the kind of content that we're trying to address today, the discussion today with the proportion. So what I'm going to do is I'm going to try to address the question sort of that was, I think, C3 or C1 rather in the written assignment. And that question was this: if you flip a coin 50 times and you get 0.6 as the proportion of heads that kind of work out, a lot of people they seem to be torn in two directions, because on the one hand they were saying, look, I feel like I should answer 0.6. That's the estimate of the probability of getting heads, but I don't really believe it. It's okay to use 0.6 as an estimate for the probability of getting heads. It's also okay to believe that's unreasonable. And it has to do with sort of the features of what we're trying to do in a situation where we don't really know much about the coin. What I'd like to be able to do is to go back and revisit that problem and talk a little bit about the universe of possibilities that we could see if we flip the coin 50 times. And the reason I want to discuss this a bit is that some people sort of suggested that we do exactly that toward the end of that problem. They were saying, look, instead of trying to think about the probability of heads, tails, or making these assignments, why not just do the experiment many times and see what kind of number the proportion gravitates to? We can think about empirical probability in this case. And that's an approach that's reasonable, but it turns out we can do even better than that if you're willing to accept simulation of the act of flipping the coin 50 times, of running that experiment, say 1,000 times, is reasonable. So the act of doing that, at least, is something that in principle can be simulated, and that's what I'm proposing to do. So let me bring up Statcrunch. I'll kind of show you what I have in mind. I got to remember to go back and share the screen. Statcrunch has some really nice features, and here's one of them. If you go to Statcrunch and go, it's not in the normal commands that you might see, but if you go over to applets, there's a lot over here. You can talk about confidence intervals, which we'll talk about later in the week. But another kind of nice thing to see is that it gives kind of a nice way of simulating at least certain things. You're not free to simulate anything you want, but certain predictable activities that people in statistics classes might be interested in, like flipping a coin. And so if you go to simulation and then you go to coin flipping, you have to indicate the parameters of the coin that you're talking about. So let's say for the sake of simplicity, for the sake of the simplicity of the exercise, I decide in advance that the probability of heads is 0.5. That's cheating in a sense, because normally we're out to say something about the probability of heads, but let's leave that aside for a minute. In order to make the example do what I want it to do, I'd like to sort of just at least say this. I feel like I have to say this. If you flip the same coin 50 times, that's the same in the sense, and then count the number of heads. The random variable associated to that act is the same random variable if you flip 50 identical coins one time. You have to kind of think about that for a minute, convince yourself that that's reasonable, but most people generally accept it. If you have questions about it, you should ask in just a second. I'm going to basically look at proportions here. So I signal proportions, some way of randomizing the data. Don't worry about that. And I hit compute. Now nothing's happened yet. So what you see here, what you're about to see is a simulation of what's going to happen if the coin is indeed fair. What would happen? What does the universe of possibilities for the proportion of heads look like under the belief that the coin is fair? And then we can look at a couple of other things. I want to analyze the data a little bit, sort of see what the variability looks like by looking at the standard deviation. But just to get to the simulation, what you see on the horizontal axis represents the proportion of heads. These are numbers between 0 and 1. What you see here on the vertical axis is the number of times that the coin, that proportion is realized through the experiment. So in our example from written assignment 4, we're imagining that the act of flipping the coin 50 times and getting 30 heads out of 50, that's one realization out of many possible things that could have occurred. And we're about to simulate what could have occurred. So does this make sense so far? Is this okay? It's just a simulation, just a simulation. So what I'm going to do is, instead of sort of ramping this up one at a time, Statcrunch is kind of useful because it allows me to run, say, 1,000 at a time. So I have 1,000 runs of the same experiment. And what I'm going to see, I hope, is kind of interesting. I see a picture that looks like this. So let's not worry about the red versus the gray. I don't really need to talk about that too much. But what I'm hoping that people see is that the universe of possibilities for the proportion looks vaguely symmetric. It looks almost like a normal distribution. You sort of see that Statcrunch helpfully locates the mean. The mean proportion is about 0.5. The expected value in the experiment of what we get is about 0.5. There's no real description of the variability, but you can also compute the standard deviation. So let's take a moment to do that real quick. When you hit analyze, what will happen is that the data set, the 1,000 runs of the experiment, their proportions are reported over here in a single column. I'd like to move this over so it just doesn't disappear from the screen. So maybe that's a good place for it right now. So the mean looks like it's about 0.5. And of course, this accords with people's intuition about the problem. If the coin is fair, you're sort of thinking that the outcome that's the most reasonable is that you get about half heads and half tails, though maybe not exactly as you see. What does the variability look like? We can calculate the standard deviation. So we calculate the summary statistics for the column proportion of heads, compute standard deviation. You maybe not be able to see it, but let me move it over. You see a number that looks like about 0.0719. So are people with me so far? You have a simulation of what you see. So in a way, this kind of answers the question, or at least it's in the direction of answering the question. If the coin is fair, what is the universe of things that can happen? We're sort of saying it looks like this. It looks kind of like a normal distribution, at least it's symmetric. The tails are very thin. Most of the mass of the distribution seems like it's centered around the 0.5. And the sort of outcome we're interested in is 0.6. There's some associated probability that we can empirically work out by just doing that. And you get 0.043. Notice that 0.043, that's about 4%. If you remember the problem that we're talking about from written assignment 4, the model also says that it should be about 0.04%. So is this okay so far? All we have is a simulation of the universe of possibilities that could occur if you flip a coin 50 times on 1,000 different occasions. Is this okay so far? Does anyone have any questions so far? That's the picture is what can happen. Does anything surprise you about it?
Can you pull up the picture one more time?
Absolutely.
Yeah, just that the distribution isn't even, that there's a little bit of lopsidedness.
Yes.
I guess that's to be expected because it's just random flips.
It's a simulation, right? Now, another to smooth it, you might do something like so if you start looking at tens of thousands of runs, maybe it gets more smooth. Does that make sense?
Yeah.
So, and you get different outcomes for proportion. So you're right to point out that I think it's looks a bit ragged. This might look a bit more smooth, more normal, I guess, right? More symmetric. But we're talking at that point maybe about 50,000 or so runs of the experiment. I hit that button many times. It's a good point. Now, the natural question is, what, given this information, what should we really do with it? And so when we're thinking about the type of problem we're going to be dealing with, the coin flip example is an example in which we're trying to say something about the sample proportion, though it's not obviously that. So it's a proportion, right? There are different types of examples in which this type of question arises. Like the crest example with the toothpaste is an example of this. If you look at many samples of 100 people, you get various different proportions. If you arrange them all in a histogram, it turns out that under some mild conditions for the problem, you get something that looks relatively normal, relatively symmetric, if the number of times that you do the experiment is large, I guess I would say. So the author kind of wants to give you a definition of the notion of the sampling distribution, and it's different things might convince you that this is reasonable. But again, the sampling distribution of the sample proportion is the thing that keeps track of the universe of possibilities for the proportion, for the sample proportion, as the sample proportion varies across all random samples. So with the thing that we just saw with the coin, it is as though we are sampling from some unknown population 50 at a time, and we're getting different proportions. But the thing to remember is that the visualization that you see, the diagram that looks symmetric, the graph that you see that's symmetric, it is the thing that keeps track of the universe of possibilities for that experiment if it's done repeatedly, if it's done in exactly the same way repeatedly. And I think that's sort of the takeaway. So I'll write some of this down. I feel like I need to, have people work on a couple of things just to sort of keep engagement. But so the sample proportion, the sampling distribution of p hat, the sample proportion is the thing it is the thing that keeps track of the values p hat can take on as the random sample varies. So, of course, p hat is a thing that can vary. It's kind of what we're saying. Under mild conditions, p hat is approximately normal with expected value p. Now remember that p was the population proportion. Like in the coin flip example, it's 0.5, and standard deviation pq over n. And so in our example, like with the simulation, we're actually seeing this. We see a peak over p equal to 0.5, right? We're assuming that the true proportion, the true value of heads is 0.5, and we estimate the standard deviation to be around I can't remember what the last number was, but let's just say it's like 0.071. Check that when you take the square root of 0.5 times 0.5 divided by 50, you get something that's about 0.0707 and some change. So again, we're seeing with that coin example, the simulation of the sampling distribution. But in general, we're going to treat something like p hat under some mild conditions as something which is normally distributed with mean p and standard deviation equal to the square root. So say in our example with the coin, we're thinking about p hat. We're thinking about not simulating. We're thinking about treating p hat mathematically as a normal distribution with peak over 0.5 and standard deviation 0.5 times 0.5 divided by 50. You can kind of see what that is. So in general, the sampling distribution of p hat, we're going to allow ourselves to believe that it looks something like that it's this nice symmetric distribution, that as the random sample varies, you get sometimes you get extreme values over here. Most of the values are kind of around p, certainly within 2 standard deviations of p. So does this conversation make sense so far? So the sampling distribution in some abstract sense is the thing that keeps track of what can happen with p hat. Because it looks symmetric, we're going to treat the sampling distribution as a normal distribution. Yes, Lily?
So when you do the, like in the parentheses of n, you have 0.5 comma, and then square root of 0.5 times 0.5 over 50.
Yeah.
Like, are those like the x, y coordinates, or like, what do you, I'm a little confused about like what that like equation would look like if it's in the, like I'm a little bit confused about.
You mean, yeah, so the standard deviation, I mean, so I guess I'll go back to what I wrote. You can try to pinpoint where the question might be. Is it here? Like these parentheses? Yeah. Okay. Yep. So when you say, so it may be just easier to write. When you write this symbol, p hat, and you see that thing right there. So remember that q is 1 minus p. When you write this, you mean to say something like this. P hat is normally distributed with mean p and standard deviation. So maybe I'll write it in terms of p. That might be a little easier. P times 1 minus p divided by n. So they're not really xy coordinates. It's a description of the parameters of the normal model that we'll use.
Gotcha. Okay.
That's all it is. And so let me sort of show you what that might look like in the coin example, just to kind of, so you can kind of see how they relate. Let me close this because it's kind of too much there. In this example, what we would kind of be saying, so I have to try to do the standard deviation calculation from memory. We'd be saying that we're going to use a picture like this to talk about the coin problem, except not this one. One where the mean is 0.5, because we're sort of assuming that the true proportion is 0.5 in this case. And the standard deviation is something like on the order of 0.0707, let's say. And you get a picture like this. It's kind of a crazy number right there, not that interested in it. But let's say that you wanted to say something about the probability of getting less, the probability that the proportion is less than or equal to say 0.6. You could easily compute that and you get a number like 92%. So that's just the left tail. So what we're saying is that we're using, or if you wanted to know, over as p hat varies, we're viewing this image as p hat. As p hat varies over all possible random samples, can you say anything about, the area, the symmetric area that sort of encompasses about 95% of the area, 95% of the samples? It looks like that, right? It's the cutoffs are between 0.36 and 0.63, several standard a couple standard deviations away from for 0.5 in either direction. You can check that. And so all this image means is that instead of thinking about the actual sampling distribution of p hat by trying to simulate it or doing something else, we're going to treat the sampling distribution, the thing that keeps track of all that can happen to p hat as you're thinking about all possible random samples. As p hat varies across all possible random samples, we're saying that we're viewing that thing which keeps track of the universe of possibilities for p hat. We're thinking about that thing as being a normal distribution, and the parameters of the normal distribution that we are using, the mean is the true proportion, like in the case of the coin, that's 0.5, and the standard deviation is some function of the true proportion p. Is this okay so far? Again, sampling distribution, if you bear in mind what it's supposed to do, a lot of what will happen over the next few weeks becomes much, much easier. Remember, it's just the thing that keeps track of how a random variable like p hat varies over the random samples. You have billions of random samples. It's as though you put them all into a histogram, and that histogram is represented, or that histogram is approximated by a normal distribution with some fixed set of parameters that we can discuss. Is this okay? It's not easy. It's not easy. Sampling distribution for students, I think, is something that's genuinely a challenge. And one reason I think that is true is because if you do an experiment, you typically only get one realization out of many possible realizations that you don't see. It's somehow the case that the sampling distribution accounts for your experiment plus all those other outcomes that didn't occur. And mathematically, somehow we know it looks a certain way. So it's not, it's not necessarily the easiest concept to get. Like, it keeps track of what happened, but not only that, it keeps track of everything that could have happened up the probability. And we can somehow use this to our advantage, which we'll see later this week. So with that in mind, I think what I'd like people to do is, let me go back to there. Okay. So I'm going to divide people up into groups. I'm going to share the screen in just a moment. I'm going to share the screen briefly and talk a little about the problems that I'd like people to consider. I don't want the groups to consider B yet. I'd like them to think a little about A, C, and D. And then maybe, too much. So we'll worry about B in just a second. There's some description of the conditions that the conditions that you need in order to replace the sampling distribution for something like p hat with a normal distribution. Here, it's sort of like we're thinking about 24% as playing the role of 0.5 if you're dealing with the coin problem. And the reason that that's important in this set of problems is that you're going to have to consider what normal model to use. So you're saying that, well, okay, the company claims that the true proportion of M&Ms, which are blue, is 0.24 across all possible bags. And so you're looking at a bag of 250 M&Ms. That's a cluster. So you're assuming that, that is a reasonable, it's reasonable to think of that bag of 250 M&Ms as representing all possible M&Ms. It's probably not unreasonable, at least, to think that. I'd like to talk about B a little bit later, maybe write down the conditions first, discuss them. But for now, just to kind of get people invested in the idea of what we're doing, I'd like the groups to try A, B, and C. We'll talk about E in just a second. But remember, the normal distribution, that's what's in play here, and you're going to have to decide what the mean and the standard deviation of the normal distribution is. But for that, remember, go back and think about the fact that we're replacing p hat with a normal distribution with mean equal with the mean equal to the true proportion, with standard deviation equal to the square root of the true proportion times 1 minus the true proportion divided by the sample size. So I guess on this problem, you have to think a little bit about what the sample size even is. So let's see. Let's give it a shot. I'll try to break people up. Oh, not 16. That's too many. Maybe about 6 rooms. The rooms are now open. It's about 1:34. I've talked for quite a while, unfortunately. So let's meet again at about 10 minutes, about 1:45, after the groups get a chance to consider these questions. So now we're recording again. So let me go back and share the screen. Okay. So in this particular case, this particular problem, you have the Mars Candy Company. They state that blue M&Ms make up about 24% of the candy sold. We're not really thinking about evaluating that claim. We're just sort of taking it for granted that that's the case. So on something like A, what are the mean and the standard deviation of the proportion of blue candies in each bag? So when you see something like this, you're imagining that the individual bags constitute random samples of size 250. And so when you look at the proportion of blue candies in each bag, you're after P hat, the sample proportion. You're trying to describe a little bit about its characteristics. Now, each bag will be slightly different than other bags. So if I pick a bag and you pick a bag, we're likely to get different values for the sample proportion. Though overall, we hope to be able to describe a little bit about its characteristics. So, if the conditions are satisfied, which we'll probably talk about in just a second, we would think, so I need to use, I think, certain notation here, so I might as well use it now. We would think that the mean for P hat is 0.24. And we would think that the standard deviation, too many symbols, but this is okay, I hope, of P hat is square root of 0.24 times 0.76. And I need to divide this by the sample size, but remember in this problem, I am treating each bag as though it is a random sample of 250 M&Ms. So I get something like this. So we're thinking about the sampling distribution being normally distributed with mean equal to 0.24 and standard deviation equal to whatever this thing is over here, which I probably need to write down in a minute. So just a reminder, I'll put this in parentheses. Under some mild conditions, which we have yet to really identify, P hat, we expect it to look like a normal distribution with mean 0.24 and with standard deviation 0.24 times 0.76. That's 1 minus 0.24 divided by the sample size of 250. So that's kind of our expectation. And from there, we can kind of build around that. We didn't do B, but we can think maybe more about C, but for that, I need to actually do the computation. So I'll pause for a moment and very quickly do this in Excel. So in Excel, I'll type in equals square root 0.24 times 0.76 divided by 250. I get a number like 0.027. So if you did this as groups, do you get a standard deviation which looks about like that? People comfortable with it? It's about right? Okay. So we'll treat it as 0.027 when we go to the normal model to try to discuss it. That's pretty close to what it is. It's good enough for our purposes. I mean, as you can see, it probably extends quite a long way. So let's go back to the question. What is the probability that less than 20% of the candies in the bag are blue? I want to draw a picture of what we're trying to say here. What's the probability that less than 20% are blue? The visualization, or maybe I do need to say this. When you make a statement that looks like this, you're making a particular claim for how the histogram of P hat looks as it varies across all possible random samples. You're saying that it looks basically bell-shaped. The peak of the bell is over 0.24, and the variability of the bell is somewhat explained by a number that looks like this 0.0270 thing. So, visually, when you're thinking about a problem that looks like this, what's the probability that less than 20% of the candies are blue? You're basically trying to figure out, so this is the representation of P hat. The peak is over 0.24, maybe 0.2 is right here. So you're basically in Statcrunch looking for the value of whatever that tail area is. So when you talk about doing the experiment repeatedly for many of the random samples, many of those random samples will result in a proportion that's less than 20%. And what is the size of or how many, so to speak, in some relative sense, of those random samples actually correspond to such a situation? Well, you can use Statcrunch to actually work that out. So let me try to do that. I have to enter my credentials. Oops. Save it. I use the normal calculator. So go to Stat, Calculators, Normal. So maybe this is a little bit better than my drawing, but the mean here that you would use is the value of the true mean, which the company claims is 24%. So just uncritically accept it. Maybe it is. The standard deviation that you're going to be dealing with is whatever we came up with over here. So we're using the number 0.027 for that standard deviation. So let me go back here. And I want to know the probability that the random variable p hat, which I'm sort of using interchangeably with x in the screen that you see right here, is less than or equal to 0.2. And so you enter 0.2 here, and you get about 0.069 or so. So about 6-7%. So did the groups get a number that looked like this? I mean, before I move on, giving people a chance to kind of catch their breath, I think that that will occur in about 7% of the samples or something like this. 7% of the samples account for that tail. Does this make sense before we move on? So the normal distribution that we're dealing with is the thing that keeps track of anything that could happen. And so in quite a few of the bags, you probably will get a proportion which is less than or equal to 0.2. And the visual, what we're saying is that, well, and how many bags would you expect this to have? About 7% of them, right? Or another way to say this is that, if you pick a bag at random, you've got maybe about a 7% chance of drawing one where the proportion of blue candies is less than 0.20. Several different ways of saying it. And so we can, I think, address the question maybe just by writing down, the probability of that. It's about 0.07, and that's sort of the thing that's the region that you're talking about. That's the area of the region. What's the probability that more than 25% are blue? This is kind of the symmetric problem. 25% in this picture is a little bit to the right of 0.24, so you're expecting it to be a somewhat less than a half. For the sake of completeness, let's just answer that question. Don't want that, something like that. We hit compute. We get about 0.35. We get a right-hand tail in this case, something on the order of about 35, 36%. So let's say that that's about 0.36. Does anyone have any questions about this so far? This is all right. Again, I don't really want to go back and do B right now. I would like, what I would like the groups to consider for a couple of minutes, for a few minutes, are the results of E and F. Maybe you haven't done that yet. It says something, it's very leading. We can assume that proportions we see less than 5% of the time are unusual. What proportion marks off the top 5% of sample proportions? You can find out where that is on Statcrunch. I'd like to sort of talk a little more about E. Maybe I'll do that when the groups come back. But what I would say about it before you start trying to do the problem, this is a bit like that question on the written assignment 4, when you're thinking a little bit about extreme events versus ones which are improbable. What E is really trying to get you to think about are, if you're thinking about an extreme event in this context as being an event which occurs in the top 5% of bags that are producing the proportion, where does that happen, right? On the other hand, you can think about F, 95% is where. Those are, reasonable outcomes. So let's break into groups, see if you can do E and F, and I'll elaborate on those comments, I think, when the groups return. Breakout rooms are still there. We will now open all the rooms. It's about 1:56. Let's come back in about 8 minutes to sort of finish up. It's about 2:04, and we'll kind of conclude the conversation at that point. So what do the groups think? Let's sort of finish up the discussion. I mean, I'll certainly write the numbers down. I'd like to talk about these things a little bit in maybe a little bit more detail than is included in the handouts, but let's go to Statcrunch. And so in this problem for something like E, sort of what I'm hoping people did is something like this. You can assume you got to be careful with that, but you have to assume the proportions that are small. Yes, is there someone? Okay, yeah, right, yes. So on E, we can assume that the proportions are less. I think it was requested that I talk about the standard deviation, so I'll write a couple of things down with that. We can assume that the proportions we see less than 5% of the time are unusual. What proportion marks off the top 5% of the sample proportions? And so when you're talking about this, remember we're treating the thing that keeps track of the universe of possibilities as being a normal distribution with certain characteristics. So visually, we're thinking about the distribution of p hat. It looks something like that. The upper 5% is sort of what we're talking about. So it's centered over 0.24. So what we're saying is that in a picture like this, what number here is associated to this image in such a way so that 5% of the sample proportions lie to the right of it. In order to do that, remember that the sample proportion that we are using is approximately normal with mean 0.24, and the standard deviation is 0.24 times 0.76 divided by 250. So my handwriting's a little hard to read, but it's a 0.24, 0.76. And when you multiply those two numbers, divide by 250, take the root, that's supposed to be the value of the standard deviation. I can maybe do that on Excel, and you can sort of replicate the calculations on a calculator if you want. I mean, I did it kind of rapidly right there. It's supposed to be about 0.027, but if you want to see where that comes from, you can type in 0.24 right here. That's the probability of success, so to speak. Blue candy found. 0.76 is 1 minus that, and the sample size is 250. And so when you put this together in Excel, hit equals, or even with a calculator, hit equals square root, open parentheses. So call that cell, that's one of the things. The asterisk command is times. So that's times 0.76. Divide the product of those two numbers by 250, close parentheses, and there's your number. So in words, take 0.24 times 0.76, divide that by 250, take the square root of whatever that is, and that is equal to the standard deviation of p hat. And we're going to wind up using it. So you sort of see a number right there. So in this example, we're sort of seeing the normal distribution that keeps track of everything that can occur. But in this problem, we just want to try to figure out what number here is associated to that 5% tail to the right. And so that's how we're judging, I guess, extreme in this context. So one way of doing that is not to put 0.25 in here, but rather put 0.05 here. And when you hit compute, the cutoff looks like it's about 0.284 and some change. That's the proportion right there. So what you're saying is that the proportion equal to about 0.28, about 0.285, let's say, 5% of the sample proportions are larger than that when you consider the value of the sample proportion ranging across all possible bags of M&Ms. So you can report here, I think that that should be about 0.284. So to the right of 0.284, that's the upper 5%. So before I move on, does anyone have any questions about this treatment so far? Calculation of the standard deviation, the use of the normal model, looking at the upper 5%. You're kind of seeing that, well, in this experiment, the upper tail, we're thinking about, there are many possible bags which could correspond to such a proportion, but that's where about 5% of them are. Is this okay so far?
Yep.
Anyone have any questions? So Lily, if you're talking, I think you're on mute.
Oh no, I was just saying, yeah, it's all good.
Okay, all right. So I think there's one sort of, you know, we've got about 1 minute left. You know, so I'll very quickly do this other problem and maybe start with maybe a more technical explanation on Wednesday. So let me go back. Let me go back to Statcrunch. Between what two values? So that's the question is maybe not totally precise. You're looking for symmetric values relative to 0.24, a right and a left value, which Statcrunch will produce. If you're trying to figure this out, 95% should be in between those two values. Go to in between. And so, you know, you don't quite want all this. But what you're looking for, if you enter 0.95 here and hit compute, what you're getting is a nice symmetric interval in which 95% of the values for p hat are found. And that's somewhere between 0.18, 0.19, say, and about 0.29. So I'm sort of hoping the group's got some answers which are kind of corresponding to this. Probably pick up here next time. I'll stay around for about 5 minutes if people have any other questions. If not, that's okay. If not, you should go ahead and enjoy your day.